Hey guys, it is Campbell here. Today we're going to be talking about finding the volumes using rotation. So if you're taking, AP Calculus, AB or BC, Calc 1, 2, whatever it may be, wherever you are, then you either have or soon will cover the topic of finding a volume by integrating. And so in this particular video, we're going to be revolving around an axis. And so that entails either disks or washers or shells. And so first, let's try to visualize the concept. There is a formula, but rather than just writing down the formula and memorizing it, let's try and figure out where it comes from so that we can apply it. Some of my students who I tutor have told me that their professor or their calculus teacher has given them the formula without really explaining it, and so they don't really understand which one to use or how to use it. So let's go ahead and start with a graph. So here are our axes, and we've got a function that looks like this. Doesn't have to look like this, could be any function. We're going to use something that looks like this, sort of like square root x. Okay, and so what we want to do is rotate this function about an axis, either the y-axis or the x-axis, or a horizontal or vertical line. For this video, we're just going to use the axes. It's very similar using a different line, but yeah, we're going to use the axes. So if we rotate this around, then we're going to get, and we look at it from the front. So imagine we're looking at it from the side right now. Imagine we rotate it 90 degrees this way, we'll be looking at it from the front. So let's try and make a sort of 3D version, right? So here's like the mirror of our function. If we come down and then up like that. So this is sort of like if we were looking at it from this direction, right? I'm standing right here and looking straight at this function. Or again, if we rotate it 90 degrees and look at it, then it's going to look like a circle. So what is the area of a circle? Well, area of a circle is pi r squared. And so how would we find the area of this circle? Well, this circle is going to have, that's going to be its radius, right? So its radius is going to be whatever the function is at this x value. Okay, so it's going to be pi times whatever our function is, f of x squared. But because we're finding volume, then we need to extrapolate this out for the whole figure, right? So how do we do that? Well, if we think of each circle, for example, this circle that we've got here, we can think of it as an infinitely thin slice of the whole figure, right? Does that sound familiar? If we add up all of these infinitely thin slices, then we're going to get the volume of this figure, or the area under this curve, integration. And so our formula, if we're going to be taking the volume from, we'll say, point A to point B, and our formula is going to be pi, right, times the integral from A to B of our function f of x squared with respect to x. Or if we were, rotating about y-axis, then it's going to be with respect to y, and it's the function of y. So that seems fairly simple. Maybe not intuitive, but it definitely helps if you visualize it this way, right? So let's go ahead and do some practice problems. Okay, so for our first practice problem, we want to take the function y equals x squared, and we want to rotate it about the x-axis. And we want to do that from x equals -2 to x equals +2. Okay, so if we want to think about this, then from -2 to +2, if we revolve it about the x-axis, then it's sort of going to look like an hourglass shape, right? It's going to be wide towards the ends, and it's going to get skinnier in the middle. And so let's go ahead and find the volume of that. So using our formula, once again, it's going to be pi times the integral from a to b of our radius, which again is going to be the distance from the axis that we're revolving around to the function, and so that's just going to be x squared, but it's going to be x squared squared. So this is going to be x to the fourth with respect to x, and of course we're doing it from -2 to 2. And so this is going to be a pretty easy one. It's going to be pi times antiderivative, which is 1 over 5 times x to the fifth from -2 to 2. And so that is going to give us 64 pi over 5. I believe this comes out to 40 point something. So if you plug that into a calculator, your calculator is probably going to give you the decimal version of the answer. So, but yeah, 64 pi over 5 is going to be the volume of this object. Okay, so for this next practice problem, we have two functions this time. We've got y equals x squared and y equals x cubed. Now, for the first practice problem, we want to rotate the area in between y equals x squared and y equals x cubed about the x-axis. So firstly, we need to find what our points A and B are. Now, obviously, we sort of intuitively know, right? It's going to be 0 and 1. But in your calculus class, especially if you're taking AP calculus, your teacher is more than likely going to have you, set where are these points equal, where is x squared equal to x cubed, and they want you to actually show how you solved it, right? But for us, we know that it's 0 and 1. So let's go ahead and do it. So we know that it's going to be pi times the integral from 0 to 1. And now it's going to be the difference between these two functions. So we need to find this area, right? But what we're really doing is first rotating y equals x squared about the x-axis, and then y equals x cubed about the x-axis. And then we are subtracting y equals x cubed, the volume of that, from the volume of y equals x squared revolved, if that makes sense. So what this would be from a generalized standpoint would be the integral from pi times the integral from a to b of our f1 of x squared minus our f2 of x squared with respect to x, or y if we go about the y-axis. Okay, so it's going to be our first function, our higher function, which on this interval is x squared. So it's going to be x squared squared, which is x to the fourth, minus x cubed squared, which is going to be x to the sixth with respect to x. Once we antiderive this, it's going to be pi times x to the fifth over 5 minus x to the seventh over 7 from 0 to 1. And so this will give us pi times 1/5 minus 1/7, which will give us 2 pi over 35. So hopefully that all makes sense. I'll go ahead and take a minute to look over that if you need. And we will do one more practice problem. All right, so as you can see, for this problem, we have the same exact functions. As I decided to not use the other example I was going to. We're going to be using the same functions, y equals x squared and y equals x cubed, but this time we're going to be rotating them about the y-axis, meaning we're going to be taking the distance between them here as an example, and we're going to be rotating it about the y-axis. And so to do that with our disk method, first we need to get a function in terms of y. So luckily this one is pretty easy, where we have the cube root of y, or y to the 1/3 equals x for this one, for y equals x cubed. And for y equals x squared, it's simply the square root of y is equal to x. So here are functions in terms of y this time. And we know that our volume is going to be pi times the integral. Now, a to b, for most functions that you use, a and b are going to be different values. For example, if you were doing square root x, there we go, and 1/2 x, or something like that, which we're going to do later in this video, then the x values here, right, your a over here and your b here, are going to be different than if you were revolving about the y-axis. Well, your a is going to stay the same, right? But b is now a different value. We'll call d. So just be careful with other functions. Because your limits of integration will not necessarily be the same. So for this one, though, they are the same, because obviously if we've got the cube root of 1, it equals 1, or the square root of 1 equals 1, and cube root 0, square root 0 equals 0. So this time we're going to have the same limits. And we are going to be using, now because we're revolving about the y-axis, we need to figure out which one has a greater x value, if that makes sense. So as we can see, the one that's further away from the y-axis is x cubed. And so that is going to be our first one. And so we actually have to use this one, though, cube root of y, and that's going to be cube root of y squared. So this will be y to the 2/3. And then minus our y equals x squared, but it's going to be square root of y equals x instead. Square root of y squared is, of course, just y. And all of this is with respect to y. And so our final answer is going to be pi over 10 when we revolve it about the y-axis. Now, there is another way that we can obtain the same volumes, but using a different method, and this is, of course, the shell method. What we just used was the disk or the washer method. A disk is just when it's one function, it's solid, from wherever your function is to the axis. A shell is like if you've got two functions and you're just rotating the area between them. But we know that, obviously, we know that if we take this area in between these two curves and we rotate it about the x-axis or the y-axis, as long as we rotate it about the axis, it's going to give us the volume, whatever the volume of the figure is when it's rotated about that axis, right? But what we have been doing so far is rotating these infinitely thin strips, these little rectangles right here, that are perpendicular to the axis we're revolving around. If we instead use rectangles that are parallel to the axis we're rotating about, which hopefully these are thick enough that you can see them, if we instead use these rectangles to rotate about the axis, we know we're going to get the same volume because it's the same function and we're rotating it about the same axis, but it'll give us a different method, or a different formula, excuse me. So what formula is it going to give us? Well, if we've got this rectangle here, and we want to rotate it about our axis. We'll go ahead and make this easier to draw for my sake, and for your sake, so you can understand it. So we're going to be taking this thin rectangle and rotating it about our axis. It's going to look something like that. It's going to be our circle, but it's going to be across the entire rectangle, right? So something like that. It'll sort of be a cylinder. And so what we're basically doing is finding the area of the circumference of this figure multiplied by the height. Yeah, I hope that makes sense if I explain it like that. And so basically our radius is still going to be this distance here, right? That's going to be the radius of the circle. But then we've got our, that's going to give us our circumference. But then we've got the height of the figure, which is going to be the distance between these two functions, right? So we stack a bunch of circumferences on top of each other, and we sum those infinitely thin cylinders, if that makes sense. So what we get, because we're working with circumference and height here, is we get 2 pi r, which is of course circumference, times the height, right? And so because these two are both going to be in terms of variables, then we've got 2 pi times the integral from a to b of our radius times our height with respect to whatever variable x or y. Okay? So let's go ahead and do some practice problems. So for this first one, we are once again going to be working with y equals x squared and y equals x cubed. So we want to rotate the area in between these two figures about the x-axis, okay? And so what that means, once again, is we're going to be taking these infinitely thin rectangles and then multiplying them by our, our radius, and then revolving them around and taking that infinite sum from a to b. And so we want our A to be the first point where they intersect, of course 0, B to be the second point where they intersect, 1. And so we are going to get 2 pi times the integral, but here's where it's going to slightly change. We are not doing x squared minus x cubed, okay? Because remember, it's the difference in x value between them, meaning we once again need these functions in terms of y. So once again, root y equals x and cube root y equals x. And because it's the difference between them, then it's going to be cube root y minus square root x. And now we also need to think, because once again our formula is 2 pi times the radius times the height. Our height, once again, the difference between these two values. And so what is our radius going to be? Well, our radius is going to be the distance from the axis we're revolving around to wherever the rectangle is that we are currently working on, right? And so that's of course going to change as y changes. So this is just going to be our y value. Our y value at x equals 0 is 0. Our y value at x equals 1 is 1. And then in between, so as we move up, right, in our integration, as we move from 0 to 1, our y value is going to be changing. And so that y value is going to be our radius. So we're going to have y again, our radius, 2 pi r times our height, the difference between the two functions, and so that's going to be y to the 1/3 minus y to the 1/2 with respect to y. This is going to give us, once we simplify it a bit, 2 pi times the integral from 0 to 1. Let's go ahead and distribute this y, so we get y to the 4/3 minus y to the 3/2 dy. And now we see, once we simplify, our answer is going to be 2 pi over 35. Now recall back to earlier in the video when we did not use the shell method, when we used the disk method, x squared minus x cubed from a to b, we also got 2 pi over 35. So this shows that it works whether we use the shell method or the disk method, that we get the same exact answer. Now, something you may be wondering that I forgot to bring up earlier in the video is, like, how do I know if it is a shell or a disk? You know, if it, for example, my professor or my teacher gives me an exam problem, a homework problem, and they say, you know, find the volume of this, you know, whether it be a single function or two, revolved around the x-axis using these rectangles, right? Because I remember my calculus teacher had problems like that. Find the volume revolved around the x-axis, revolved around the y-axis, using the rectangles that are parallel, or the rectangles that are perpendicular. Oops. Hello? Perpendicular like that. And so my calculus teacher taught us like a way to remember it, sort of a rhyme, and that is parashell and perpendicular. So remember that disks and washers are the same, so it works for both of them. But parashell sounds like parallel. So if you're using rectangles parallel to the axis that you're rotating, meaning, you know, like in this problem we just did, we used this infinitely thin slice, right? The difference between cube root x and square root, or cube root y and square root y. The difference between those in that slice is parallel to the x-axis. So we use the shell method. But if they tell you to use the perpendicular rectangles, so you've got this infinitely thin rectangle and it is x squared minus x cubed, then that is disk. Perpendicular is perpendicular to the x-axis. So I hope that helps. In terms of deciding, like if you get a free choice rather than you need to figure out which one they want you to use. If you've got a you know, a washer like this, then the shell method is often a good choice. But because both of them give you the same answer, it's really up to you. You know, you're given a function like this. If you think, hey, the you know, the inverse is, or I mean, not the inverse. Yeah, the inverse. The inverse is going to be easier to work with, or the original function is going to be easier to work with. It's really a matter of personal preference. Okay, so for this next practice problem, we are going to be rotating y equals square root x, or I guess the area in between y equals square root x and y equals 1/2 x. First, we're going to rotate it about the x-axis, and we're going to be using the disk method. So I'll give you a minute. Go ahead and try and solve this one using the disk method. Come back when you think you have your answer. So welcome back. If you've just done this practice problem, then because we're using the disk method, remember that it's going to be our big radius, which is for this going to be root x, minus our little radius, which is 1/2 x. So our big radius squared, root x squared is just x. X over 2 squared is x squared over 4. So we've got x minus x squared over 4. And because, I'm not sure I mentioned this earlier, but we're going to be rotating the area bound by where they intersect each other. And so that is going to be 0 and 4. Again, root 4 is 2, and 4 divided by 2 is 2. So that's where they intersect each other. So our bounds are going to be from 0 to 4. It's going to give us 8 pi over 3. Now I want you to do this same problem. We're going to be revolving it around the x-axis, but this time using the shell method. So go ahead and pause the video, do the same thing using the shell method, and come back when you have your answer. Right, and so coming back, we should have, because we are using the shell method, remember Paris shell, we are using the circumference times the height. So our height is the difference between these two functions, but it is the horizontal distance rather than the vertical distance. So we need them in terms of y. So if we just square both sides, then we get y squared equals x. If we multiply by 2, we get 2y equals x. So we've got 2y and y squared. 2y is further away from the y-axis, so the higher x value. And then y squared is the smaller x value. So we should have, oh, and of course, y, as we move up and down, y is going to be our height. So we've got 2 pi times the integral. Now our boundaries are 0 is going to be the same because obviously 0 times anything is 0, and the square root of 0 is 0. And when we flip them, 2 times 0 is 0, and 0 squared is 0. 0 is going to be the same. Now, instead of 4, which was our boundary for the disk method, we're going to be using 2, because again, we're integrating with respect to y, and 2 times 2 is 4, and 2 squared is 4, which will give us our x value. So our bounds are going to be from 0 to 2 of 2y minus y squared times y. And so when we distribute the y, then we get 2y squared minus y cubed from 0 to 2. So it is 2 pi times our whole expression. And in the end, we will get 8 pi over 3, which matches what we got with the disk method. So this is pretty much it for finding volume by rotation. If you want, I can probably do a video just on practice problems alone, because in this one we pretty much only used algebraic. We did use radicals, but for all intents it's essentially algebraic, polynomial type integration. And so those are fairly easy. When we're using stuff like the natural log or e or sine, it can get a bit more tricky. So yeah, if you'd like, I can go over some practice problems in a separate video. I'm also going to be covering finding volume with cross-sectional shapes. So this is sort of cross-sections where the cross-section of our shape, when we rotate it out, right, is a circle. But when your teacher gives you a problem that is like, you've got a shape like this with cross-sections, triangles with a height equal to their base, right? So finding those like geometric cross-sectional volumes. But yeah, so this is going to be it. If you guys have any questions, feel free to leave a comment. If you found this video useful, please consider leaving a like and subscribing for more stuff like this. I'm hoping to do more chemistry pretty soon, but math is super easy to just crank out because there's so much math and it's wonderful. But yeah, so hope you guys enjoyed, and I will see you next time. Bye.